All right, we are recording. Yay, it works. Thank you, Mr. Ron. There you go, on screen. Thank you, Mr. Ron. All right, so we're starting really the second semester of pre-calculus. The first part of pre-calculus is advanced algebra, kind of an algebra 3 stuff you've seen before. And the second semester, which was starting kind of late here, but of course the first semester was really short, is basically trigonometry. Trigonometry. And of course, trigonometry is a single word, but it is made up of several words. Try, right? Try means give a darn, put some effort in. Or in this case, it means 3. So give 3 efforts. 3 efforts, 3 efforts, 3 efforts. Gone means maybe your work ethic has kind of left you this year already. Okay? You're getting senioritis from some of the seniors, so it's gone. And so you're going to try to regain your work ethic. And then me means that it all starts with you. Right? If you point at somebody, you have 3 fingers pointing back at yourself. So be careful when you do that. And then, of course, there's that word again, try. So it refers. So really, trigonometry just means I need to work harder. I need to give more of a darn. That's what trigonometry means. Not really. Okay? Well, man, it works in nicely into today's after-test discussion, doesn't it? Okay, again, if it stings, if you hear it coming to you and it stings, maybe it's supposed to sting. But if it doesn't sting, it's water off your back. It's like, it doesn't apply to me because I'm either doing well or I just don't care. Oof. How's the cake? It's great. Let me try another piece on camera. There's no camera. Here are the words. Metry. Where have you heard that before? Geometry, right? Geometry. Trigonometry. What does metry mean? Psychometricians. What does metry mean? Infer from context clues. Measure. Okay, and this context clue is reading what I already wrote there. Measure. So a geometer is someone who measures geos or earth measurer, right? Geometry deals with the study of shapes in a coordinate plane. You're measuring things. Trigonometry is the measure of trigonos. The heck is trigonos? Angles. So guess what trigonometry is in a nutshell? It's the study of angles and their measures. Yeah, so trigonometry is, let's go ahead and write it out. It's the study of angles themselves and their measures. Which means now we need to start talking about how we're going to measure an angle. But I guess we need to first define what an angle is. Okay, an angle equals, what is an angle? Anyone want to tell me? That's angle, not angel. Angle. What's an angle? In your own words, not mine. What's an angle? Good question. An angle, let's see. You had angles in geometry. Let's go back to earth measuring, geometry. You have something that looks like that. I'm going to rotate a little bit. There we go. You have this shape right here, which is called a ray. It has a fixed end and it has a non-fixed end. It goes out to infinity and definitely in the other end. If you take another ray, which if they're people, you might want to give them nicknames because then it gets confusing when you call both of them, hey, Ray, and they both turn. But in this case, we have another ray that share a vertex. 2 rays that share a vertex form at least one angle. Okay, and the angle is going to be in between them. And so what an angle is nothing more. It gives us a way to, an angle is a measure of blank between 2 rays. Now, if I took out my ruler and I measured from this point on the ray to this point on the ray, would that give me the angle? Well, what if I measure from this point on the ray to this point on the ray? Would that give me the same measurement as the other one? No. So, first of all, we need to talk about what we're measuring. We're not measuring the distance between 2 rays. Because that varies, right? The further out we are, even if we go straight across, the distance is going to vary. And that should just be one angle, right? So regardless of where we measure, it's going to be the same. What are we actually measuring when we measure an angle? It's a measure of blank. Where blank is? No, we're not measuring degrees. Usually that's temperature. Like this morning I got up, it was 39 degrees Fahrenheit outside. That was a measure of the temperature. We're not measuring temperature here. Nice try, though. What are we measuring? You can learn a lot by reading. Keep that in mind. Ah, very good. You can learn a lot by reading. It's a measure of rotation. That's what we're measuring here. You talked about torque. Torque has to do with rotating, right? Perpendicular to a plane or to a line. We're measuring rotation. So if I started one of these rays, let's do the one on the bottom, and I rotate over to the other ray, and I'll draw it like that. The arc implies that we're kind of rotating from one point onto another point through the same radius. But I could also rotate from the blue ray a little bit higher back towards the other ray, and I'll draw the arrow that way, and that should be the same rotation. Even though physically, if you're traveling along the different arcs, one of them is longer than the other, the angles are the same. So that is what we're measuring. We're measuring the rotation. And it's the same anywhere between any points on the ray, two rays. Okay, now, how are we going to measure rotation? We don't measure it in feet. We don't measure it in miles, inches, no units of length. We measure it in what, Mr. Pierce? Measured in degrees. Good. So a degree, which we write like this. We put it as kind of like a superscript here, like an exponent, and it's a little open circle. I call that the degrubble. Let me go ahead and just write that like this. I call it the degrubble, which is a portmanteau of two words, degree and bubble, because I get tired of saying degree bubble. But notice there are no Fahrenheit units associated after that. There are no Celsius units associated after that. So degrees Fahrenheit is a specific unit. Degrees Celsius is a specific unit. But degrees without Fahrenheit or Celsius behind it does not measure temperature. It measures what? Rotation. Yeah. So the degrubble, that is the units. The existence of that little open circle is the units for degrees. And it's a measure, it's a unit of measure for an angle. Now, if you had to describe to me what a degree is, other than a unit of measure of an angle, I need some quantifiable relevance or frame of reference to compare something. So let's come back to this little angle that I drew up here. First of all, I don't want to keep referring to it as the angle between the two rays, so we're going to name it. And the first letter that we're going to get used to naming is that letter there, which refers to not only the name of the angle, but also the measure of the angle. They're interchangeable. We're going to call that, it's the Greek letter for the th sound, theta. Okay? Other Greek letters that we use, alpha, which is looking more like an A. Some people, you know, they put the little Jesus fish on their car backwards, and like, no, it's not backwards because fish can swim both ways. Okay? And that's fine. I can see the top fish is swimming left and the bottom fish is swimming right. But maybe there's a double entendre there, right? Because not only does it represent a fish, but it represents an alpha. And alphas cannot be drawn both ways. That's what this is. An alpha has to be swimming left because it looks kind of like our letter A, which does not swim to the right. So just keep that in mind. We can also use this letter, which I really love. This is my favorite Greek letter. It's like a capital B on a pogo stick. That's a guy who knows how to have fun. Right? Reminds me of like Tigger, the way Tigger gets things done. We call that beta, or just beta. So alpha, beta. Those are the first two letters in the Greek alphabet. How would the song go for them? Alpha, beta, alpha, beta, gamma, delta. It's a weird song. Yeah, it's very different from our song. Okay, we could use any number of letters, though. We typically stay with Greek for the beginning purposes, though. That is either phi or phi. I tend to call it phi with a long I. Not fo or fum, though. That's something different. Later on, though, you're going to see that we just get back to plain old x. X makes a good variable that represents angles. But for right now, I'm going to stick with theta, maybe alpha, beta, phi. What would be then a plausible measure in degrees for our theta? Plausible, based upon your geometry experience. Wait, you just said something. What? You're complimenting me. That was a few days ago. You said I was what? Acute angle. Thank you. I'm less than 90 degrees. Okay. So what would be a number less than 90? 89? 45? 30? It looks a little maybe bigger than that. Let's go 30. 30 degrees. Good, right? Degrees. So in the absence of that degrubble there, you just put 30. I might think theta is 30 what? 30 Egyptian race car drivers? I don't know. Oh, degrubble. 30 degrees. I got it. Units are important. Do you think you'll lose points if you don't put units on degrees? Yeah. Okay, cool. So that's 30 degrees. Now, how do y'all know that? It is reasonable because geometry. So what is a degree? 30 is in the context of what? 360 degrees. A circle. Okay, so let's talk about that. You just said that a circle is 360 degrees. So if I say draw me 360 degrees, you would draw a circle and vice versa? The shape of the tires on your cars are 360 degrees? A circle is 360. It's 360. A circle is 360 degrees. Why? And what do you mean by is? So if I start somewhere on the circumference of a circle, and I rotate from, let's say, some starting right here, and I rotate all the way around back to there, you're going to say that theta is what? 360 degrees? Okay. I've heard that before. That's what first period kept saying. I'm kind of curious why you said 360 and not 100, because 100 would seem like it'd be a really good number. 100, right? It's a nice decimal number. We like things in powers of 10 because we have 10 fingers. That's what the whole metric system is built on the power of 10. So you chose 360. That seems a little arbitrary. Why'd you choose 360? Random, just kind of like out of the blue. There's no rhyme or reason. What? Oh, it has 4 right angles as opposed to 4 wrong angles. What's a right angle? 90 degrees. So you're saying that 90 goes into 360 evenly? 400 times? 4 times? Okay, I like that. 360 has 2 of its integer factors, 90 and 4. Okay, is that the only reason? Because 100 you could use 25. Why isn't a right angle 25 degrees? That would have been cool, right? 25, 25, 25, 25. That's 4, 25. That's a buck. That's 100. That's a full rotation. What? The unit circle has something to do with 360. You can learn a lot by reading. Yeah. You had your special right triangles in geometry, right? Your 30, 60, 90. 30 is a nice number. 60 is a nice number. If you go way back to the ancient Babylonians, okay, the ancient Babylonians did not use base 10 like we do, which is interesting, okay? We like base 10 because we have 10 fingers. The ancient Babylonians used a sexagesimal number system, which is base 60. And you know why they used 60 as the base? Not because they had 60 fingers, but because 60 was sexy. It was very sexy. 60 is a sexy number. In fact, try and say the sexagesimal number system without saying sex. Yeah, we're talking about sex today, people. The sexagesimal number system is base 60. It's very sexy. What makes a number sexy, Tate? It wears lingerie. No, I'm not asking you anything else, Tate. No. See? 60 is sexy because, like 360 divides evenly into 4 quadrants of 90, what are some of the integer factors of 60? 1, 2, 3, 4, 5, 6, Not 7. Darn. 8, 9, 10, 12, 15. 60 has lots and lots and lots of nice integer factors. And you got to think back to the Babylonians. They didn't have computing devices, so they like to work with whole numbers. Base 60 gives them a lot of opportunities to break things down into parts that are still integers. Okay, so that's why 60 is sexy, because it has lots of nice integer factors. Okay, well that explains 60. Do we still see any sexagesimal stuff? So any carryovers from the ancient Babylonians here today? Or did we get rid of it? Time. Time is a carryover from the ancient Babylonians, right? How many minutes in an hour? 60. How many seconds in a minute? 60. You ever wonder why? Ancient Babylonians. It has to do with the rotation. 60 is also a factor of 360, which is nice. So if 60 has a lot of factors, so does 360, yeah? Whoa. So if you're trying to break a circle down into parts, 360 has a lot of nice partitions that are still integers. But still, so does 400. Why 360? 60, full circle, right? Full circle. You start someplace, you go all the way around, and they call it coming full circle, right? You come back to where you started. Like, ooh, it's kind of chilly. And then time goes by, and it's like, now it's warm. And then, oh, it's getting chilly again. Must be that time of year, that day in Texas, where it's cold outside. Seasons, right? They come at regular intervals. Now, we know that that happens here on planet Earth every 365.25 ... days, right? We have very, very accurate ways to take into account the fact that it's a decimal, right? Every 4 years we add another day, unless it's divisible by 4, and then we don't. So that's taking into account those other decimals after the 0.25. But back then, they didn't have Shutterfly, but they still had cute calendars. And then they would say, oh, it's fall again, right? Everything would come full circle. What does that have to do with 360? Yeah, that's the approximate number of days in a year, which is kind of cool if you think about it. So at the very first meeting of what to partake or what to break a circle into, 100 might have come up. Maybe 60 came up. Maybe 5 came up. That guy didn't have a chance. But someone said, hey, since it's a circle, it comes all the way around again to the beginning, and like 360 days in a year. Well, okay, that's easy to remember. The school kids will be happy. It'll be easy for them to remember that. Okay? So that's hypothesized as to one of the big reasons why there's 360 degrees in a circle. They didn't know that first period. Kind of nice if you would have been told that on day one, right, of degrees. But anyway, it's kind of cool. Now, later on, when they learned that they were actually 365.25 ... they didn't go back and change that to the number of degrees in a circle, did they? Like, then Tony Hawk would have done, like, not a 900, but like a 905 ... Do you see that new Tony Hawk trick? He did like a 905 ... No, I didn't see that. We still call it a 900. Why did we not change the number of degrees in the circle to reflect the actual number of days in the calendar year? Right, it's not as useful, first of all. Plus, people are already kind of used to it, right? We're kind of using it already. Don't change courses midstream, right? In the panthological expanse of time, we're always midstream, I guess. People are already used to 360, and 360 has a lot more factors. So anyway, that gives us a way now to define what a degree is. 1 degree, also known as 1 degrubble, is what? 1/360th of a full rotation. And so rather than define a circle as being 360 degrees, that's like, that's an after effect. In fact, we define a degree in terms of the partition of a circle. 1 degree is 360th of a full rotation. Now, if you multiply both sides by 360, you do get 360 degrees equals 1 rotation. Which means now if you divide both sides by 2, a half rotation is 180, and that's a nice integer. And I could maybe pull that trick off back in the day, 180 on the skateboard. What's half of a half? a fourth of a rotation, which is what, Rylan? Yeah, you were referring to that earlier. So one of the big differences between geometry and trigonometry, that is Euclidean geometry versus analytic geometry, is we are going to take angles like this, which is a 30-degree angle, and we're going to standardize it, because maybe you didn't draw yours like that. If you take this right here and you stretch it or compress it like this and you rotate it around, which we can easily do with Notability. See that? Look at that. Whoa! Does that change the angle measure when I do that? It doesn't. The measure of rotation is still the same. So all of those angles are equivalent in geometry. Now, it's going to be hard to all be on the same page if everyone's drawing angles in different configurations and sizes, right? So guess what we do in analytic geometry? We do this. We take the following. We put it into standard form. This is kind of getting a little bit ahead here, but it'll work. We need two rays. So what we do is we systematically say, okay, we're going to put the vertex of the two rays at the origin. And because we need one ray to start with, we're going to call that our initial ray. It's going to be the positive x-axis. So we're always starting on the positive x-axis. Now, to redraw my angle of 30 degrees there, what I'm going to do then is draw my second ray right around here. We call that the terminal ray. What does terminal mean? The bus stop, the bus terminal. It's where the bus stops. The terminal means end. It's going to be right there, and we're going to rotate that way. And we're going to say then that that is another representation now of 30 degrees, but now everyone will have it drawn the same way. Now, could you then have gone down and drawn that 30-degree angle in quadrant 4? Sure. But here's the deal. Angles now in this class are going to be vectors and not just measures. So if you rotate in the counterclockwise direction, like we did, from the positive x-axis, we're going to call that the positive direction. Against the clock is positive direction. If you were to rotate downward down here, that would be theta equals negative 30 degrees. If you rotate clockwise, that's going to be considered negative. Very interesting. You couldn't have negative angles in geometry because you were talking about interior angles of a shape. But now negative angles make sense here. I forgot my degrable. I'll get used to it again. So now if I ask you to draw a 30-degree angle in standard form, everyone's going to draw the same one up there. If I ask you to draw a negative 30-degree angle in standard form, everyone's going to draw the bottom one. So we have a vector now. Here's another reason we want to draw the arc. The arc shows the direction we're traveling with the arrow, but let's come back up here. If you didn't draw that arc right there, and you didn't label it, and you said that that angle is 30 degrees, that's not necessarily true, right? Because if you didn't specify which angle, could that also be an angle? Yes, let's call that alpha. And you probably didn't think about that in Euclidean geometry because, again, you kind of looking at angles as like interior angles of shapes. So you didn't talk about angles a lot that were bigger than 180, but we can certainly have them here. In fact, if this angle here is 30 degrees, based upon what y'all said about going full circle in the ancient Babylonians, what would be a plausible measure for alpha? We're not on the Euclidean or coordinate plane here. It'd be 330 degrees, both positive in this case. You don't talk about vector and quantities until you're on the coordinate plane. So in the Euclidean plane, you could call that a 330-degree angle. Now, is there a name for two angles that add up to 360 like there is for 90 and 180? Complementary would be great, right? Because complete, one complete rule. I would, if I were there, I would have voted for complementary to be 360, but that's 90. Supplementary adds up to 180. I don't know, Google it. Theory, two angles that add up to 360 are? Palm Pilot, doesn't work that way. I don't know. If you find it, let me know. I don't know offhand what the name is. If there isn't one, we can come up with one like we did the Grubble. All right? So anyway, what is now a single degree? It is 1/360th of a full rotation. So you measure rotation now in degrees. But you could also now measure rotation in parts of degrees, right? It doesn't always have to be a full degree. So let's jump down to example 1. It says to draw an angle of 76.425 degrees. Let's go ahead and get in the habit of drawing it in standard form. I know I haven't really introduced that in the notes yet, but that way you're kind of establishing good habits from the beginning. So draw an X and Y axis. The positive x-axis is always going to be our initial ray, the starting ray. And 76 degrees is a rotation that measures, in this case, if it's positive, so I go up or down? Clockwise or counterclockwise? Counterclockwise. Counterclockwise. So I'm going to go ahead and give that a name of theta equals, and I'm going to go ahead and call that theta. By the way, it's easy to remember because all your life you've learned that this is quadrant 1, right? But where was quadrant 2? Straight down or to the left? Quadrant 2 was to the left. That seemed a little weird, wasn't it? And that was 3 and that was 4. Why do you think the quadrants are numbered that way? They go with the positive rotation of the angle. Yeah, in standard form. You rotate through the quadrants in the numerical order. Quadrant 1, and then you get quadrant 2. That's the positive. All right, so there is your angle theta. Now notice that it's 76 full degrees and 0.425 of another. There is a way to measure fractions of a degree other than this way. This is called decimal degrees. Okay, you have 76 full degrees plus 425,000 of another full degree. Decimal implies base 10, not base 60. But there is another way to represent fractions of degrees, just like there's a way to represent fractions of an hour. Right? If you tell your friend or ask your friend, hey, yo, how long was you waiting for me? He'd be like, I don't know, about a fifth of an hour. And you'd be like, I have no idea how long that you were waiting for me then. How long were you waiting? A fifth of an hour. Dude, what does that mean? Do the math for him. How long were you waiting? 20 minutes? 40 minutes? A fifth of an hour? 12 minutes. See, thank you for doing the math. I had no idea. You tell me you're waiting for 12 minutes, I know how long you're waiting. You tell me like a fifth of an hour, and I'm like, who speaks like that? I need to get new friends. Gosh. You're waiting 12 minutes. 12 minutes is reasonable, right? That is how you represent a fraction of a full hour. Same thing if you ask your friend how long you were waiting, and they said, oh, about a fourth of a minute. Which is what, buddy? 15 seconds. There's ways to represent fractions of minutes as well. Same thing with decimal degrees. You don't have to measure it in decimals. You can measure it in what's called, believe it or not, minutes and seconds. Sweet. So when you represent an angle that is a fraction of full angles in degrees and minutes and seconds as opposed to decimal degrees, we call it DMS, which is degrees, minutes, seconds. And here's the conversion. You're going to love this. 1 minute is equal to 60 seconds, just like with time. And one degree, smaller unit, 1 degree is equal to 60 minutes. So really all we're doing is we're substituting the word hour with degree. An hour is 60 minutes, a degree is 60 minutes. A minute is 60 seconds, same here. So we have conversion factors. We use single tick marks for minutes, and we use double tick marks for seconds, and of course we use the degrubble for degrees. So we can establish what's called a conversion factor. Yay, conversion factor. Conversion factors are really, really useful because they are equivalent to 1. Not equal to 1, but equivalent to 1 with their units. And you can use those for dimensional analysis, also known as stoichiometry. So let's go ahead and convert 76.425 decimal degrees into degrees, minutes, seconds. Here's how we're going to do it. 76.425 degrees. We know that's going to equal 76 full degrees, right? I'm going to write down the 76. It's the 0.425 I'm after. So 0.425. Let's come over here and say 4.25 degrees. I'm going to put it over 1. All I got to do is use conversion factors. Well, if I want to convert from degrees to minutes, 1 degree is 60 minutes. Here's the beauty of stoichiometry. You can put the conversion factors however you want. So if I want degrees, degrubbles to divide out, I have degrees in the top, I'm going to put a degrubble in the bottom. And if I want minutes to appear, I'm going to use the single hash mark for minutes instead of min, the units I want to appear, I'm going to put in the numerator. What's the conversion then? 60 minutes is 1 degree. If you needed to have that flipped, it works the same way. 1 degree is 60 minutes. It's just an exchange rate. They're equivalent. And notice the degrees divide out and you're left with minutes. Well, you would probably instinctively know how to do that, right? If I said a fifth of an hour is how many minutes, or I'm sorry, a half of an hour. Let's do that. That's easier. 0.5 of an hour. A half of an hour is how many minutes? 30. You know that instinctively, but if you didn't, you would just say, oh, 1/2 of 60 is 30. You'd multiply. Same thing here. What's 0.425 times 60? If you have your calculator, it wouldn't hurt to get it out. I'm going to show you the keystrokes, though. 0.425 times 60. It comes out to be 25.5 minutes. Okay, so now I know that 76.425 degrees is the same thing as 76 degrees, 25.5 minutes. So I'm going to write it back over here. These are the same. When you go from degrees to minutes, you don't put any punctuation in between them. There's no comma, there's no plus sign, you just kind of write it separately. But guess what? I now have a fraction of a minute. I have 0.5. So I could do the same thing. I can convert minutes down that are parts of minutes to the next unit down, which is seconds. So you would do this. Now you would just take the fractional part again, 0.5 minutes over 1. And now you want minutes to divide out, so you put minutes in the bottom. You want seconds to appear, so you put it in the top. And there are 60 seconds in 1 minute. Doing that stoichiometrically, notice that your minutes divide out, and you're left with seconds. Now you don't need the calculator for this, because what's 60 times 0.5? 30. And it terminates. That's seconds. So here we go. We can finally write our answer all the way through 76.425 decimal degrees is equal to 76 degrees, 25 full minutes, and then 30 seconds. Oops, I put the bubble again. Minutes, seconds. These are identical ways to measure that angle in degrees. One's decimal degrees, one's degrees, minutes, seconds. Now, where have y'all seen notation like this, degrees, minutes, seconds? ROTC people, map reading? No? Anyone here? Anyone here got a cell phone? Smartphone? Yeah. That's exactly what it means. You navigate the globe using latitude and longitudes, and you can figure out your GPS coordinates at any point on the globe by using a latitude and a longitude point. That's measured in degrees, minutes, seconds. Degrees, minutes, seconds. So navigation uses degrees, minutes, seconds. And now you know what it means. And I'll show you later why we even use degrees at all for navigating the globe. It has something to do with where we rotate out of the center of the Earth, which is very hot. Very hot. Okay, now there's another way to do it on your calculator. Y'all know how to convert from decimal to fraction, right? If you have 0.125 on your calculator, you know how to just hit math, enter, enter, math, enter, enter, math, enter, and it converts it automatically for you. Your calculator will convert automatically from decimal degrees to degrees, minutes, seconds. So here's another way to do it. If you have a calculator, type in 76.425, and I'll go ahead and show you how to do that. And I'm going to put the units there. Your calculator can convert it directly for you. 76.425. Now, you don't have to put degrees on there, but if you go to your angle menu, it's under second apps. Apps is 2 buttons above the 7. If you hit second apps, it's your angle menu. And look what number 4 is. There's that characteristic arrow, which means convert to. This will convert it to DMS, which of course stands for degrees, minutes, seconds. So if you type in your angle in decimal degrees, go to your angle menu, which is second apps, number 4, hit enter. It'll show you that, then hit enter again, and look what it does. Oh, sweet. Thank you, calculator. So I'm okay with you doing that as long as you can explain to me maybe how to do it without the calculator. You're basically taking the fractional part, multiplying by 60, writing it down, taking the fractional part, multiplying by 60, and writing it down. And if you ended up with, by the way, if you ended up with fractions of a second in your final answer, like you ended up with like 30.3 seconds, we don't take the 0.3 and convert it down to the unit below seconds. We'll just leave it as 30.3 seconds. Hello, Tyler, you want some cookie? Hurry. Mm-mm. Mr. Corby's birthday. All right. What do you need? Want? What do you want? All right. Let's try converting the other way very quickly. New Braunfels, Texas. Anyone ever been there? There, it's lovely. Here are the GPS coordinates of New Braunfels, Texas. I don't know where in New Braunfels, Texas this is. If it's right there on the city square, or if it's like in the mayor's living room. I have no idea. I don't know where they measure it from. But it's 29 degrees, 42 minutes, 10 seconds north by 98,727 west. Those are your latitude and longitudinal coordinates, all right? So, respectively, latitude is first. I want to convert 29 degrees, 42 minutes, and 10 seconds into decimal degrees. Unfortunately, your calculator will not convert it for you. So this is one that you might have to do on a quiz. You're going to convert them all in one fell swoop using dimensional analysis. The 29 is already in good shape. So it's 29 full degrees plus. Now you've got two different things to convert. I need to convert the 42 minutes back to degrees. So 42 minutes, if you want to put it over 1, what's the conversion factor? Well, I want my minutes to divide out, and I want degrees to appear. So it's 1 degree now over 60 minutes. And notice your minutes divide out, and you're left with degrees, which is what we wanted. And then you do the exact same thing for the next one, plus 10 seconds, put it over 1. Now for seconds, you can go through minutes. 1 minute is 60 seconds, and that'll get your seconds to divide out. But then you got to convert the minutes to the degrees. So then you'd have 1 degree is 60 minutes. So notice you're dividing by 60 twice. You could also divide by 3,600 once if you want to do that. 1 second is 3,600. 1 degree is 3,600 seconds, just like an hour is. So really, all you're going to type into your calculator now is exactly what you see in one fell swoop. 29 plus 42 divided by 60 plus 10 divided by 60 divided by 60. Here's what it would look like. 29 plus 42. We're dividing by 60 now instead of multiplying. We do it once for the minutes, plus, and instead of like doing it in sequence, multiplying by 60 twice, we're going to take the seconds and just divide by 60, boom, twice. Divided by 60, divided by 60. And you get 29.702 or 703. Now notice, because we have to actually not list all the decimals here, the degrees, minutes, seconds answer is actually considered more accurate. Don't forget your degrubble on the end. So if you want now, what I've had students do in the past, you can text your parents and let them know once you find out the other one. Just say that you know New Braunfels coordinates are at 29.703 and 28.124. It's interesting. Your parents know that you love them if you do that. All right, be ready for a quiz on Monday, converting back and forth between the two. That gives you an incentive to start your worksheet. Just those problems. Explementary? Explementary angles. Like that? Not an A? Explementary angles. Those add to 360? Thank you so much. I've never known that. I learned something today from you.